Or maybe you guys are just more spread out. Okay. Anyway, it is now 10 past, so let's go ahead and get started. So welcome back. I clearly didn't go fast enough to scare you all away yesterday. So let's continue going on. My first announcement is, I mentioned a moment ago, I will speak really, really quickly unless you interrupt me. So this is my open invitation for you to interrupt me if I ever start talking too quickly. So what did we do last time? We started talking about how most points in a hyperball are near the surface. So this is a little bit unintuitive, but you can sort of see what happens. Like as you increase the dimensionality, the relative amount of surface area increases compared to the volume of your object, right? So today we're going to show a couple other things which are also a little bit unintuitive. So the first thing we started doing last time was most points in a hyperball are near the equator. So what does that mean exactly? This means that most points are orthogonal to the North Pole, wherever you define it. And this will also imply that basically every pair of points is orthogonal, and not just that, but even if you have lots of points all together, they're all mutually orthogonal with some high probability, assuming your dimensionality is high enough. So this will imply that sampling from a sphere that is generating random directions is hard. And so we'll show how we can use Gaussians to help us resolve that. Now, some of the naive methods for sampling from a sphere or ball don't work so well in high dimensions. And so we need other more clever ways of resolving that issue. Unfortunately, I don't think we're going to have time to get to the Gaussian annulus theorem or Johnson and Strauss today, just because it turns out there's a lot of material to prove. But that will be next Wednesday. And that is sort of the culmination of this first week of the course, is how randomness and Gaussians can be helpful. So any questions before we get started? Okay, let's dive right in. So as I mentioned, we're trying to show that most points in the unit ball are near the equator. And we're also going to talk about something, the dot product, which you guys should remember. Basically, that is a signal of how orthogonal two vectors are. So last time I said that if A dot B is small, then that means that A dot B is nearly orthogonal. So strictly speaking, this isn't quite true. A and B could both just be really tiny vectors. And so we really want to add an additional condition and the norm of A and norm of B are not that small. And like this is all very hand wavy, but the basic idea is if A and B are, but this is something that we have because we know that A and B are both near the surface with high probability. And we'll be a little bit more rigorous about this, but basically, not only are most points near the surface, most points are all orthogonal to each other. So everything's at a right angle in high dimensions. One sort of intuitive way of thinking about it is there are lots of different ways you can be at right angles when you're in high dimensions. This is a right angle, this is a right angle. If you had another dimension going out into the fourth dimension, that would also be a right angle, and things like that. So there are many different ways of being at right angles. And so that's sort of the intuition behind how most things can simultaneously be at right angles to each other. Okay. So what did we do last time? We fixed a particular unit vector as north. So we fixed the first coordinate as north. It doesn't matter what you pick. And what we want to show is that most of the volume is concentrated near the equator. So that is to say, want to show that most of the volume of the unit ball, most points in the unit ball have the first coordinate is less than or equal to, well, something. What did I have here? I had 1 over the square root of d, I think is what I wrote down there. Is that what I want? We'll run with it for now. So first, I'm going to mention, like, there is this big O notation, which those of you who've taken algorithms will be familiar with. If you haven't, I'm going to briefly recall it here. Since this is something we will be using a lot in this class, just recall big O notation. A function is O of g of n if there exists some constant c greater than 0, such that for all n, f of n is less than or equal to c times g of n. So basically, we're saying that f of n grows no faster than g of n. We also have a couple other notations. F of n is, so big O is what we'll be using most often. We also have omega of g of n, which just says that there exists some constant c greater than 0, such that for all n, f of n is greater than or equal to cg of n. So basically, f grows faster than g of n. And another one, which is f of n is theta of g of n, if both are true. Both if it is both f of n is O of g of n and is omega of g of n. So the two grow asymptotically at the same rate. And lastly, we have f of n is little o of g of n if the limit as n goes to infinity of f of n over g of n is equal to 0. So basically what we're saying there is that f of n grows much slower than g of n. So what we want to show is that as dimensions as we increase dimensions, the equator gets fatter, taking up more volume. So does that make sense? Well, let's start by drawing out, I don't remember if I drew this last time, but let's start by drawing this out. So if we start with in one dimension, and we want to look at the equator, that's basically all the regions around here. I've drawn this vertically just so that it's a little bit more obvious what the equator is. So that's the 0 point. And so this is the amount of stuff that's near the equator. Whereas if we're in 2 dimensions, well, then we have all of this stuff that's near the equator. So this is in 2D. And in 3D, let's draw that out. We have, this one's a little bit harder to draw, but let's see if I can do it. So we have everything along the equator there. So as we increase dimensions, sort of intuitively, the equator gets fatter because it gets an additional dimension in which to, well, get fat. And so that takes up more volume. And this allows us to prove this nice theorem. This is 2.7, theorem 2.7, which is for some constant c greater than or equal to 1 and d greater than or equal to 3, so dimensionality of these 3, we have at least 1 minus 2 over c times e to the minus c squared over 2 fraction of the volume of the d-th dimensional ball of, I think I called this b sub d. So the d-dimensional unit ball has the first coordinate is less than or equal to c over the square root of d minus 1. For any vector, so any coordinate x, x vector in b sub d. Okay, so that's what we're going to try to prove. And so this proof is going to involve basically just counting in some sense. So we're going to be doing a couple integrals. So let's prove this. So by symmetry, we just need to consider the top half. By symmetry, consider just the top half. Because of course, half of the ball is above the plane and the other half is below it. So, okay, so we're going to let A be equal to the set of vectors in B sub D, such that x1 is greater than or equal to c over the square root of d minus 1. So basically, this is the set of stuff that is far away, which is above the equator region that we've defined, where we're defining the equator to be anything that's within c over d, the square root of d minus 1. And we're going to let h be equal to the set x vector in b sub d, such that x1 is greater than or equal to 0. So this is just going to be the upper hemisphere. And now we want to compute some volumes. So what do we want to do first? Well, let's compute the volume of A. So what's the volume of A? So note that the volume of A is just equal to the integral from c to 1 c over c divided by the square root of d minus 1 to 1 of 1 minus x1 squared d minus 1 over 2 times the volume of b sub d minus 1 dx1. What do we mean here? Well, let's break down this integral. So this here is just the volume of unit radius ball of lower dimension. And if you want to draw this out sort of pictorially, if we have some sphere here, my spheres are not particularly nice, but they'll have to do. So if we have some sphere here, what we're saying is that if we're going up to some particular point and looking at the sphere here, or sorry, the circle there, well, this is a right angle. And this distance here is 1. And this distance here is whatever coordinate this is along the first coordinate. And then this here will be the radius of this circle that we're cutting out. So that'll be the square root of 1 minus x1 squared by the Pythagorean theorem. And so what we want is we're going to vary x1, and then we're going to integrate over it and just look at the amount of stuff that's in each of these circles, and we're going to add them up. So standard calculus 2. And so what we're going to do is we're going to take the volume of a ball of radius, ball of dimension d minus 1 of radius 1 minus x1 squared, the square root of that. And so when we do that, we need to scale down the volume of the ball, of course, by that scale factor. So we're scaling down by the square root of 1 minus x1 squared. And so together, these give us the volume of radius square root of 1 minus x1 squared, ball of dimension d minus 1. And of course, we're just integrating over all the different possible values of the first coordinate. So integrating over x1 coordinate. Okay, so now we're going to do a series of approximations. So let's say this entire thing is less than or equal to some integral. I'm not going to set the bounds yet. Well, actually, the integral is from 0 c to 1. And we're going to say that instead of using, we're going to replace the first part with e to the minus d minus 1 over 2 x1 squared times the volume of b d minus 1 dx1. And we can do this, of course, because we know that 1 minus x is less than or equal to e to the minus x. So we're just using that known inequality. And so we're plugging that in. The next thing we're going to do is I'm also going to change this up. So you notice that now, all of a sudden, this piece here is always positive. And so since it's now always positive, we can say that's less than or equal to integral from c to infinity. Because that's clearly strictly less if anything, if the stuff in the integrand is always positive. So we can just integrate and integrate to infinity. So note that we have to do that particular inequality we have to do after we've changed the integrand so it's always positive, or else things don't work out as nicely. Okay, but now once we've done that, it's just a matter of computing this integral. Let's do another inequality. So this is going to be an inequality. Oh, sorry, that is not c. You guys should stop me when I make mistakes like this. C divided by square root of d minus 1. Okay, so let's keep on going. So this is less than or equal to the integral from c times divided by square root of d minus 1 to infinity of, let's see, x1 times the square root of d minus 1 c e to the minus d minus 1 over, oh, sorry, messed that up. This is minus d minus 1 over 2. This is there. So that negative sign is actually important for it to be in that position. X1 squared times the volume of b d minus 1, dx1. Does anyone want to tell me why I could do that? Just want to make sure you guys are following. Yeah, exactly. So because the stuff I've thrown in there is always greater than or equal to 1. And so this is because that's by one of our conditions up here, which is we are integrating in this ball. So by these conditions, we know that this is because x1 square root of d minus 1 divided by c is greater than or equal to 1 in A. And so we can substitute that in, and our inequality still holds. Okay, now that we've done that, that makes the integration a lot easier. First, we bring stuff out in front. So this is all pretty standard. Times the integral from c over square root of d minus 1 to infinity of x1 e to the minus d minus 1 over 2 x1 squared dx1. I'm not going to bother going through all the substitutions, etc. But when you do this, what you end up getting is you end up getting that this is just the volume of b d minus 1 times square root of d minus 1 over c times minus 1 over d minus 1 e to the minus d minus 1 over 2. Sorry, I keep on putting a negative sign in the wrong place. So x1 squared from c over square root of d minus 1 to infinity. And this is just going to be equal to the volume of b sub d minus 1. So the d minus 1 dimensional ball divided by c times the square root of d minus 1 e to the minus c squared over 2. And this now here is an upper bound on volume of A. So we have an upper bound on volume of A. And the next thing we want to do is, well, we want a lower bound on the volume of H, which is the upper hemisphere that's contained with, the upper hemisphere of the ball. Because we want to see what fraction of the material is contained along the equator, right? And we're not going to do it too carefully. Of course, you could explicitly compute it, but then, of course, you can't use the technique we just did because that was an upper bound, and so you need to do something different in order to get a lower bound. But also, we have that the volume of H is greater than or equal to the volume of all points x in H, such that x1 is less than or equal to 1 over the square root of d minus 1. So, I mean, that's just true. Like, you're restricting the size of your ball and size of your hemisphere, and so you're going to get something that you're going to get a lower bound. And this is greater than or equal to the volume of a ball of size d minus 1 times 1 minus 1 over the d minus 1 to the d minus 1 over 2 power times 1 over the square root of d minus 1. What have we done there? So what we're doing is, if you look at, go back to our circle, we only care about the upper half playing, which is this. But what we can do is we can draw a cylinder. So we can draw a cylinder. Actually, let me do that in a different color. So we can draw a cylinder that goes just here. And clearly, the volume in the upper half playing, the volume in the upper hemisphere is bounded by the volume of the cylinder. And that's all we're doing. So we're bounding it by the volume of the cylinder. And this is going, when we do that computation, that's going to be greater than or equal to the volume of b sub d minus 1 divided by 2 times the square root of d minus 1. Note that we're also going to use that 1 minus x to the a power is greater than 1 minus ax for a greater than or equal to 1. Okay, so this gives us a lower bound on the volume of the upper hemisphere. And so now we can get a bound on the fraction of material that is in the lower hemisphere compared to the amount that's compared outside of the range that we care about. So then we know that volume of A divided by volume of H is less than or equal to, you plug all these things in, it gets a little bit messy, but we've arranged things to cancel out nicely. Volume of, so plugging all these things in, e to the minus c squared over 2 over volume b sub d minus 1 divided by 2 times square root of d minus 1. And what you end up getting is 2 over c times e to the minus c squared over 2. So you'll note that the fraction of material that's in A, which is this area above the equator, compared to the total amount of area in the upper hemisphere, well, is some small exponential. And so depending on what constant c you choose, of course. And so what this means is just that you don't have very much material that is away from the equator, which completes our proof. Okay, did everyone follow? So that was a simple integration exercise. You just measured how much stuff was in any part of your sphere. So now we have a couple things. So plus, we know that so we now know that most of the volume is near the equator, and we know therefore most of the volume is orthogonal to the North Pole. We also know that most of the volume is close to the surface, and so most of the volume has close to the unit norm. And so this means that most points are orthogonal to the North Pole. And you might think, oh, well, if this is true, then that means that most points are orthogonal to each other, right? Because the North Pole was arbitrarily chosen. And so if we just chose random pairs of points, you just assign one of them as the North Pole, and with high likelihood, the other point is orthogonal to your first point. And that's exactly what we're going to do. In fact, we're going to prove something even stronger than that, which is that if you have a collection of n points with high likelihood, assuming you chose the dimensionality and your constants correct, every point is orthogonal to each other. And this, you can just use a simple union bound from probability form. So let me make that a bit more rigorous. This is theorem 2.8. So consider drawing n points. And I'm going to try to use the vector notation, but if I forget, please tell me and I'll add it in. So we have n points in B to the B sub D uniformly at random independently as well. Uniformly at random. Then with probability 1 minus O of 1 over n. So what are we saying here? We're saying that with probability almost 1, except you're subtracting out something that is at most of size 1 over n. With that probability, we know two things. One, we know that xi, each of our xi's, so each of our points has a norm greater than 1 minus 2 log of n over d for all I. So this is true for every single one of our points. And we know that the dot product between any two vectors, any two of our points, is less than or equal to the square root of 6 log n divided by the square root of d minus 1 for all I not equal to j. So we're just going to formalize what I said a moment ago, that even if you had a collection of a bunch of points, with high probability, they're all orthogonal to each other. So let's prove the first part first. Well, this is really easy because, for any fixed I, for a specific value of I, the probability that I'm going to write this as, so the norm is less than 1 minus epsilon, is less than or equal to e to the minus epsilon d. And so this is just by our earlier theorem where we talked about the volume is near a surface. And therefore, the probability that xi, the norm of that, is less than 1 minus 2 log n over d is less than or equal to e to the minus 2 log n divided by d, which is just equal to 1 over n squared. And now you'll notice that I chose epsilon very carefully. What did I choose it to do? I chose epsilon so that when I use a union bound, it precisely becomes just 1 over n. So by the union bound, and for those of you who don't recall, the union bound just basically says that if I have a bunch of different events, the chance that all of the events happen is, well, the chance of all the events happening can't be higher than the chance of each individual, all the individual probabilities summed together. So this basically says that the probability that there exists some I such that xi, the norm of that, is less than 1 minus 2 log n over d. Oh, did I write something wrong? There is some chat message. Shouldn't it be e to the minus 2 log n? Oh, that is quite possible. So did I plug that in wrong? So where was I? Yes, yeah. So, yep. So I plugged that. That was incorrect. Yeah, thank you for the correction, Nelson. So the probability that there exists an I such that this is true is less than or equal to 1 over n, because we have n points, and you're just basically looking at probability that any one of them breaks your assumption. Okay, and 2. So the lab basically shows that everything is near the surface, and we're just going to use the same argument again about the dot products. So by theorem 2.7 above, we know that the probability that x I dot e sub 1 is greater than c over the square root of d minus 1, which is less than or equal to 2 over c e to the minus c squared over 2 for any fixed I. Okay, so what we're saying is that once you fix a north pole, then everything is small, like the dot product of it, most things are near the equator. And what else we can say is this implies that the probability that we just plug in the value for c we chose. So again, that was carefully chosen to cancel things out. So that probability that this is greater than the square root of 6 log n divided by square root of d minus 1. So we're letting c be equal to the square root of 6 log n. This is less than or equal to 2 over the square root of 6 log n e to the minus 3 log n, which is equal to 2 over the square root of 6 log n times 1 over n cubed, which is O of 1 over n cubed. So we don't care about the log factor. We only care about the like n cubed tower here. And note, of course, that this is true for any north. True for any north. And so note that when we look at all the different pairs of items, there are n choose 2 pairs. N choose 2 pairs, I and j. So for each of the pairs, we're just going to define, we define, let's say xj over the norm of xj as north. Okay, so we're normalizing it so it's unit norm, but it doesn't really matter so much. You're basically saying, well, just pick one of the 2 directions as north, and then the other direction, well, it's going to be near the equator, or given that particular north pole. And note that n choose 2 is smaller than n squared, and so we're going to use the exact same union bound argument. So by union bound, for all I not equal to j, the dot product condition fails with probability at most O of n choose 2 times n to the minus 3, which is equal to O of 1 over n. And this completes the proof. So basically, with high probability, if you just choose n random points, they're all going to be orthogonal to this degree of orthogonality that we've defined. They're all going to have approximately unit norm. So now you might be wondering, well, this is all cool and unintuitive, but why does it matter? What really interesting things does this imply? Does anyone have any suggestions about why this might matter if you're a data scientist? Why does it matter that most points are orthogonal? Why do you care? Do you care? Okay, yeah, so this is a little bit like, it is unintuitive, but it's a little bit esoteric, right? Why does it matter that most points are orthogonal? And there are a couple of different reasons. One is sometimes you might want to choose some set of points as something like a basis. And so then you want a bunch of points that are almost orthogonal. And this is an easy way of doing it. But you might be like, well, I know another easy way of doing it. I just use the standard basis. And we'll see a couple of examples why in some cases we don't necessarily want that. But one super interesting corollary of this is that it turns out that because most points are orthogonal, we can prove that the volume of a unit sphere goes to 0 as the dimension gets bigger. So let me say that again. If you have a unit sphere, all we're doing is we're adding dimensions to it. The volume of that thing actually goes to 0. Not it gets small relative to a unit cube, but actually it limits to 0. And so let's see that happen. So our corollary is that the limit as d goes to infinity of the volume of b sub d is equal to 0. Now this particular fact is really not obvious. This is not obvious. How is it not obvious? Well, let's look in low dimensions and see if we can see this kind of behavior happen. So what happens in low dimensions? Well, if we're in low dimensions, let's say we're in dimension 1, and we have 0 here. This is -1. This is 1. Well, what's this volume? Just 2, right? So volume is equal to 2. What about if you have a circle with unit radius? Well, what's the volume of that? Just pi, because pi r squared. And if we have a sphere, well, the volume of this is equal to 4/3 pi. And one of the things you might notice is, well, it doesn't look like the volume is going to 0. In fact, this volume is gets bigger as the dimension goes up. And so what I'm claiming right now is that if you keep on doing this, if you keep on adding dimensions, eventually it'll approach 0. And there are a number of different ways you can show this. One of them is you could explicitly do all the integrals and actually calculate what the volumes are. But another way of seeing it is this is actually a consequence of the other couple of theorems we've proven about where all the points are. And so, which is a neat little proof. So I'm going to show it to you. So the proof here is we're going to choose some constant c that's equal to 2 times the square root of log of d. Okay, so what we have is that by theorem 2.7, at least a 1 minus 1 over the square root of log d e to the, I think this is minus 2 log d. Yeah, minus 2 log d is equal to, and this thing is equal to 1 minus 1 over d squared square root of log d. A fraction of the volume has x1 is less than or equal to 2 times the square root of log d over the square root of d minus 1. Okay, so we're just saying, oh, well, everything's near the equator. We knew that. Next, this implies that for x, some randomly drawn point from b sub d, so randomly drawn, the probability that the norm of x1 is greater than 2 times log d over square root of d minus 1 is less than 1 over d squared square root of log d, which is of course just less than 1 over d squared. For d big enough. Like obviously if d is equal to 1, then things go wrong. So we're going to ignore that. Okay, so now we have that. What we're going to do is we're going to do something a little bit clever. We're going to let C be a box or cube or a hypercube with side length 4 times the square root of log d over square root of d minus 1, centered at the origin. So at this point, you might notice what I'm doing. So what I'm doing is I'm basically saying, okay, so we have this cutoff, basically. We're saying most things are near the equator. And what we're going to do is we're going to then cut off along each of the different equators. So each of the different axes, we're going to cut off and build a box out of just the equatorial region that is on the equator of every single one of these circles. And then we're going to ask how much volume is in that equatorial box. So, if we have some other point, let's call it Z, which is in the intersection of C and B, so that box as well as this, our original ball, then Z sub I is going to be less than or equal to 2 times log d over square root of d minus 1 for all I in 1 through d. Now we're going to use the union bound again. So by the union bound, we know that the probability that the norm of that xi is greater than square root 2 times the square root of log d over square root of d minus 1 for all of the I. Well, that is less than 1 over d, because the probability that any one of them was less than that was 1 over d squared. The probability that all of them are less than that is less than 1 over d. And you note that this is less than or equal to 1 over 2, so long as d is greater than or equal to 2. What does that mean? Well, that means half of the ball is in the box. So we've drawn this box now, and what we now claim is half of the ball is in the box. And let me write that out. So this implies that the volume of C intersect B sub D is greater than or equal to 1/2 the volume of B sub D. But now, what's the volume of C? So, but we know that the volume of C, well, it's just a box, and so it's pretty easy to compute the volume. It's going to be 4 times the square root of log d over square root of d minus 1. And since that's the case, to the d power. And so that's equal to 16 times log d, sorry, that's a 16, not a log. 16 times log d over d minus 1 to the d over 2 power. And that actually goes to 0 as d goes to infinity. And you know, this is because if you look at the denominator versus the numerator, the denominator has an actual d and the numerator only has a log d. And so you take that to some big power, this is going to go to 0 as d goes to infinity. So that box that contains half of our hyperball has a volume that goes to 0 as d goes to infinity. But since it contains at least half the volume of a hyperball, that means the volume of the hyperball must also go to 0 as d goes to infinity. Goes to 0 as d goes to infinity. And that completes that proof. So why does this matter? Well, suppose I ask you a question. How would you sample a random direction in high dimensions? Now, what does that exactly mean? So if I ask you to sample a random direction, I might be like, well, suppose I have some high dimensional thing and I want to go in some particular direction, and I have some algorithm that requires that I turn a random direction and go that direction for some distance. It turns out that this means that sampling is going to be hard. Because one easy way you might think of to sample random direction is, well, that is precisely sampling along the hypersphere, right? All you're doing is you're sampling a particular direction along a particular point on the hypersphere. And if you could sample from the hyperball, then all you have to do is project out to the hypersphere, and then you'd have a direction vector. But we can't do that. And the reason for that is because this volume goes to 0. So let me write that all down. So how do we generate directions randomly? So that is to say sample points from the sphere. So now if you're in 2 dimensions, well, one solution to that is, well, you can start here and you sample a point. So one solution is to sample the ball and project out the sphere. So if I sample the ball here, then all I do is I project out, and that gives me a random direction. So now how do we sample from the ball? So how to sample from ball? So one naive method, oh yeah, go ahead. So that's a really good question. Why can't you just sample from the space and divide in? Does anyone else want to answer that? Or yeah, go ahead. Yeah, it won't be uniform. Because if you look at, let's actually see that. So let's suppose I had a unit box. Okay, and I have a, let's even just do this in 2 dimensions. I have a circle that's inscribed in this unit box, right? So if I'm sampling in the space, that's effectively sampling from this box, right? And what happens is, if I sample, well, I might sample a bunch of points here, and those are all fine, but some of our points are in each of these corners, right? And so it turns out that if you just sample randomly from this box and keep all those points, when you project down, you end up getting a lot more mass here than you do here. And so you don't get a uniform direction. Instead, you're biased towards all of your corners. So you can't do that. But that actually does get at one of the ways that you might naively try to sample from the ball, which is, well, we have a very easy way of figuring out if something is in a hyperball, right? You just take a look at its norm, and if the norm is less than 1, then it's in the hyperball. And so this brings up, so one solution to this, which I'm going to call a naive solution, but this naive solution actually works pretty well in low dimensions. So people do this. So I'm going to call it the naive solution, which is that sample from the space, so from a covering cube. And then the step 2 is reject points outside the ball. Outside the ball. And sometimes you might call this a variant of, you might see this called a variant of rejection sampling. And so basically it takes that intuition, well, you can sample from the space pretty easily, and then we do need to be careful about uniformity, and so we just discard any points that fall outside of the ball, and then what we're left with is something that is uniformly distributed in directionally inside of this ball, and then you can just project out, and then you're happy. And this works pretty well in 2 and 3 dimensions, but sometimes it doesn't work so well. And one of the cases where it doesn't work so well is when d is really, really big. Because as we just showed, as d goes to infinity, the hyperball gets volume 0. And so you're never going to get something that's acceptable, and so rejection sampling is going to take forever. And so this fails in high dimensions, fails in high dimensions, I should say. It works well in low dimensions. Fails in high dimensions because volume of b sub d goes to 0, and volume of cube goes of the cube that be inscribed in goes to 2 to the d. So the volume of the cube is getting infinitely big, the volume of the ball is getting infinitely small, and you're not a happy camper. Luckily, there are ways of resolving this. And so we'll come back to rejection sampling a little bit later, actually, when we start talking a little bit more about Markov chains. And there are ways of sort of adapting these sorts of methods to work well, depending on the structure of your problem. But it turns out that this particular problem, that just doesn't work very well for. Luckily, we have other things we can use. And so now we're going to go back to random Gaussians, which we talked a little bit about last time, and we're going to talk more about on next Wednesday, which is that Gaussians have lots of really cool properties and that make life easy for, well, everyone. So Gaussian variables. To sample, we're going to directly sample directions, actually, instead of sampling from the ball. And then later, we're going to sample from the ball by first sampling a direction and then sampling a radius. And so we're actually going to go the opposite direction in order to do both of these sampling problems. So Gaussian variables. And so note that the probability density function of the 1D Gaussian is P of x is equal to 1 over square root of 2 pi times the exponential of minus x squared over 2. Okay, so this is a Gaussian. And one of the things you might notice is that all of the sort of x dependency is up in this exponential. And that'll actually turn out to be really nice because it turns out when you multiply exponentials together, you just add together their exponents, right? So what is, if we have a Gaussian point, so let x vector be equal to a set of random Gaussians, where each of our coordinates, xi, comes from the normal distribution with mean 0 and variance 1, IID. Well, then we know that the probability density function of this entire vector is going to be equal to, well, all of them are sampled independently. And so you just multiply together all the BDFs and you get 1 over these 2 pi to the d over 2 power. So the d over 2 power times the exponential of, and so when you multiply all these together, you're adding together all the different coordinates. This is minus x1 squared plus dot 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 plus x sub d squared over 2. So what can you tell me about this PDF? Exactly, it depends only on the norm. It is spherically symmetric. And so if you swap any two of the coordinates, so long as the total norm is still the same, you're still going to get the same value. And so this here is spherically symmetric. So when we're sampling the hypersphere, we normalize the unit length to unit length x over the norm of x. And that gives us a point along the sphere. Because all we had to do was, like, the reason we were sampling from a ball to begin with is because balls are spherically symmetric. And so that means that any direction is equally likely, right? And so here we have some other distribution that's also spherically symmetric. And that means that all different directions are also equally likely. And so then we're left with a random direction. And so this allows us to sample from the hypersphere. But now, of course, we solved the sampling from a sphere problem. But now we also need to go back and sample from a ball, because sometimes it's useful to just sample a random point from some high dimensional ball. And to do this, we're going to, as I said, we're going to go the opposite direction. We're going to start by sampling a direction. And then all we need to know is we need to know what probability it has of being at any particular radius. And that's something we can figure out by just looking at how much of the volume is contained within the hyperball in the different shells of different radii. And we've already computed that a couple times, but let's do that again. So we need to know the volume in each shell. So let's see. You sample from Hyperball. We need to know the volume in each shell. So if you drew this out, so we have some Hyperball. We want to know how much is in each of these shells. Okay, where this is the shell of radius r. So, well, let's see. What's the volume of, we know that the volume of the hyperball of radius r is just r to the d b sub d, where b sub d is the unit ball of d dimensions. So this is equal to r to the d times the volume of b sub d. So this here is the volume in ball up to radius r. And we want to know how much it changes as r varies. So we just take a derivative. So d dr of r to the d times the volume of b sub d is going to be equal to d times r to the d minus 1 times the volume of b sub d. And so we can use this value here as the PDF of the radius, as PDF of radial coordinate. And so what we end up with is we're going to let rho be a random variable with probability density function with PDF. P of r is going to be equal to dr to the d minus 1 for some r in 0, 1, because of course we're sampling over radii of radial coordinates from 0 to 1. Then all we have to do is then take y bar, or y vector, is equal to rho times x vector divided by the norm of x to get a random point in b to the d. Okay, and this is one of the reasons why it's important to have a better intuition for what's going on in this high-dimensional geometry, because sampling directions is a very natural thing you might encounter in a number of different applied math examples. So maybe you're a robot and you're doing path planning and you want to sample a direction. If you're a 3D robot, that's not so bad. But if you're a 10D robot, then it gets a little bit worse. I'm not always the best at coming up with the applied examples. I'm not a roboticist. But there are examples where you want to sample from these high-dimensional directional distributions or a high-dimensional ball. And for those cases, you can't use the same intuition that works in low dimensions, because in low dimensions, the geometry just has intrinsically different behavior than when your dimensionality gets higher. But this intrinsically different behavior can be used at times for other purposes. And that's one of the things we're going to be seeing next week on Wednesday, where we're going to show that the sort of weird behavior of these Gaussians and weird behavior of high-dimensional geometry allows you to do really clever things in projecting down from high dimensions to low dimensions, where our intuition works a little bit better. So that is where I think I'll end the class today. I think I'm a couple of minutes early, actually. But yeah, that's a very natural stopping point. And so on Wednesday, we'll finish up the section on high-dimensional geometry and Gaussians and Johnson and Strauss, and then we'll move on from there. I will post a homework assignment sometime over the weekend, probably. It's not going to be that long. This is not a core class. This is a topics class, but there still will be homework, as I've mentioned. So with that, does anyone have any questions before ending class? Yeah, go ahead. Oh, I haven't decided yet. You'll have at least a week from when I post it. Oh, you'll be handing it online. So everything will be handed in online. There will not be a point at which you will hand me a physical piece of paper unless you really, really want to. I would prefer you to just hand it in over, like, I haven't decided if I'm going to be doing it over Quercus or CrowdMark. It might even actually depend on the assignment, but I'll send out all that information out whenever I send the problems out. So, well, class dismissed. Have a good weekend, and I will see you on Wednesday. Oh, yeah, yes, yeah. I'm also going to make all these notes available afterwards. So, yeah, so this will all be posted online. Yeah. Okay, let's see. I am going to shut down the video, so bye to everyone in chat.